The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Our next presenter is Farshad. He's an associate professor of civil engineering at Penn State. He has 17 years of teaching and research experience in support of sustainable civil infrastructures that are safe, durable, reliable, cost-effective, and environmentally positive. Farshad, please.
Okay, thank you very much, Sarah. Good afternoon. It's a pleasure to be here. All right. So the work that I am going to present essentially is a part of, or is a subset of results that was from a research project, a collaboration between Penn State, QES, which was a consulting engineer partner, as well as PennDOT, who was both a technical partner as well as this research sponsor. That larger project, some of the objectives of that project was to identify the causes of early age cracking in concrete and bridge decks, essentially relying on field data, inventory of bridges in Pennsylvania to look at some of the causes of early age crackings and effective mitigation strategies for early age cracking. And then take that a step further to figure out what is the effect of cracks on durability and long-term performance of bridge deck. And through some of the work that we've done, actually, we address this third problem to some extent, but we also put in procedures in terms of data collection procedures for PennDOT that now they are actively monitoring crack development over the bridges in their biannual inspection, so they can look at how a certain extent of cracking would result in a speed of deterioration in bridges. Other than that, the work involved developing a bridge database and deterioration model based on 30 years of condition data for a large inventory of Pennsylvania bridges, and finally to identify the most cost-effective remediation practices based on the life cycle cost of the structure to determine what's the best way to repair and what's the best time to repair. These objectives were accomplished in 6 tasks: literature review, survey of DOT personnel, field evaluation of bridge decks, which is primarily what I'll talk about, this item 3, the bridge deck database and deterioration modeling, life cycle cost analysis, and finally development and dissemination of the research products. So this, I'm sure this is not news to anybody in the room, that the work on early age cracking of concrete, or research in the field of early age cracking of concrete, is not new. It's been going on for 30 or so years, and there's a lot of good quality research data that supports some of the causes of early age cracking. So in this slide and the next slide, I'll try to summarize in a kind of a very condensed version of what we found in the literature. First thing is that it's been found and kind of confirmed repeatedly that the primary cause of early age cracking is restrained volume change, as opposed to things like traffic loads and other types of mechanical loads. So essentially what we have, and our previous speaker also referred to this, is that we have, for example, a concrete deck that is cast in place over a girder, and the concrete naturally would like to shrink or contract after it's been cast. This could be a thermal contraction after the concrete temperature peaks, around time of setting, and then cools down to the ambient, and it also could be because of drawing shrinkage or autogenous shrinkage. However, the girder doesn't want to shrink, and as a result of this, we cause this restraint effect, tensile stress, and cracking in the concrete deck. In a very simplified version, deterministic, there is the dashed line shows the strength development in concrete, and the blue line shows the stress development. When the stress exceeds the strength, we have the cracking. There's been a lot of work in looking at this in a kind of a non-deterministic way and looking at a statistical variation of both stress and strain and getting a window of cracking time or probability of cracking as opposed to a single time of cracking. But just looking at this very simplified version of the event, we can see that the increased contraction, increased shrinkage, and increased stiffness of the concrete would lead to higher stress and higher cracking. So increased contraction could be, for example, when a concrete has a higher paste content, that would shrink more. Or if it has a higher cement content and a higher heat of hydration, so the thermal contraction will be more. So increased contraction, as well as increased stiffness, or the elastic modulus, or compliance or inverse of compliance of concrete would impact the amount of stress that generates in concrete. So the concretes that are stiffer, that are higher strength, somewhat counterintuitive, would be more prone to cracking. Okay, so some of the key information that gained from the literature review. One is that to minimize the early age cracking, we have to limit the total amount of cementitious materials or paste content. 28-day strength, which has a large impact on the stiffness of concrete, as well as slump. And there has been good work, including the very good work at the University of Kansas, that shows that higher slump concrete could be more prone to things like sediment cracking and so on, or excessive slump in concrete. Optimizing aggregate gradation would help with reducing the paste content and therefore reducing the cracking. Use of supplementary cementitious materials primarily through reducing the heat of hydration and thermal contraction, and also it has another advantage of increasing the resistivity of concrete. So once the concrete cracks and once you get the salts at the level of rebar, the resistivity of concrete would help slow down your speed of corrosion or rate of corrosion. Enforce proper moist curing, so that helps reduce the overall shrinkage and also delays when the shrinkage happens. Limiting rebar size and spacing, again, helps in controlling the cracks. And there was some mention on concrete girders maybe preferred over steel girders, and I'll talk about that more in our data. Also, the literature suggests that cracking shortens the corrosion initiation. It makes sense. You get cracks, the salts can get direct access to the rebar. But it's interesting that chloride buildup off the crack seemed to be more important than on the crack. And the reason for this has been suggested that right at the crack you can get some corrosion and get some corrosion products which effectively seal the crack, or at least seal the tip of the crack right where it intersects the rebar. And it seems like until the other parts of the rebar starts active corrosion, you don't get a lot of corrosion happening. To reduce the risk of corrosion, use minimum 2 inch of cover and supplementary cementitious material. And any remediation action has to take place before active corrosion starts. So once we are past the corrosion initiation period, repairing is not going to help us much because the steel underneath is going to keep corroding even if you repair the surface. So most of these are based on lab work, and what we did is that we wanted to essentially, again, look at the field data and the actual bridges that PennDOT owned. We looked at a little over 200 bridges, including 163 new bridges, as well as 40 older bridges, and primarily we looked at crack inspections. Mapped the cracks, measured the length of the crack per unit surface area of the deck, both at the time of construction as well as 1 year after construction. For the older decks, we did crack inspections. We also did the coring and measuring the chlorides. So the crack inspection was, we used this to get something that is called crack density, which is the length of the crack per unit area of the deck. It's shown, the unit would be, for example, yard per square yard of concrete. We looked at both longitudinal and transverse cracks. We looked at positive and negative moment areas of the crack, of the deck. And we generally, this project happened in the span of 2013 to 15. We followed the Federal Highway Administration protocols that was most up to date at the time, that include measuring the crack density, measuring the delamination by sounding the deck, coring, measuring the chloride content, and looking at the rebar status. The coating happened both on crack and off crack, so we had a rebar locator that we could determine where the rebar is. We, again, took samples from the concrete at the level of rebar. We determined the chloride content. We looked at the condition of the rebar. This is probably one of the worst looking rebars that we could find. Fortunately, not a lot of PennDOT decks were in this shape, but all right. So let me show you some of the results. First, I'm going to look at the crack density results. So here we have a graph that shows, let me talk about the one on the right. Here you have three types of concrete. These are kind of PennDOT classes, AAA, AAAP, and HPC, and the mean crack density that we have here. And each of them is shown in terms of the total amount of cracks and the longitudinal and the transverse cracks. Before I spend more time on this, let me introduce you some of these concrete classes that PennDOT uses. We're looking at only these three rows, AAAP, HPC, and AAA. You can see over here that the structural design strength of these are, all three of them are 4,000 psi. So the amount of strength that we need from a structural engineering standpoint is the same. However, the PennDOT specification requires AAA to be over-designed at least by 500 psi. So this is designed at 4,500. And the maximum water-to-cement ratio is 0.43 as opposed to the other ones that are 0.45. There's also some information about the minimum and maximum cement content that was in the PennDOT specification. So let's go back to this slide. So here, the graph on the left, we see the strength of these three classes. We see the AAA, the mix that was at the lower water cement ratio, designed at to have a higher strength. It did have a higher strength, and interestingly, it also cracked more. Quite a bit more, you can say, comparing with these two. We have the strengths at 7 days and at 28 days. It looks like the mix that had the least amount of strength, the HPC, also had the least amount of cracking. All of them meeting the 7 or 28-day 4,000 psi structural design strength. If we look at, this is the same graph that we saw before. This one shows the amount of the total cementitious material content, the total Portland cement content, and the total SCM content. So the light orange and white add up to the dark orange. We can see the AAA that cracked the most had the highest amount of total cementitious material. And between the other two, the HPC, which cracked the least, had higher SCM replacement in comparison with the AAAP. So it looks like lowering the strength helps. It looks like capping the maximum cementitious materials is good, and also replacing, within reasons, Portland cement with SCM is helping. And that's primarily through reducing the heat of hydration and reducing thermal contraction of concrete. We also looked at out of the 163 decks, about a third of them were placed on steel girders and the other ones on concrete girders. And it looked like we found that it seems to be a significant difference between the cracking density of the two. We did not explore the cause of this much further. It could be due to the stiffness of steel. It could be due to, maybe temperature development in concrete and how much of this is synced into steel and so on. But it looks like, just based on field data, that pre-stressed concrete girders are doing better. We also looked at two methods of construction. One of them is called a half-fit construction, which means that you have a deck and you close down half of, you are repairing let's say half of the deck longitudinally and direct the traffic on the other half, which is the half-width construction. And the full-width construction is that essentially you have a detour and move all the traffic off the deck, do the repair or do the reconstruction. And it looked like the half-width construction resulted in a lot more cracking. Okay, now let's move on quickly to the chloride data. So this is kind of a raw data on the chloride content from the 40 older decks. Obviously, the new decks, the chloride contents were none or very small. So here we have, as a function of age, the chloride content, and we can see both the on-crack and off-crack data points. We use this data to determine the effective diffusion coefficient of chlorides into the concrete, which is this graph. And we have the data, again, both off and on crack, so we can, for example, see this at the same age, most likely the same bridge, we have, let's say over here, 2 off crack and 1 on crack and so on. And for these, we also figured out a ratio of the on-crack to off-crack. And we see that for most decks, that ratio is somewhere between 1 to 4. So it looks like the cracking can accelerate the diffusion by up to a factor of 4. Okay. We also looked at the black rebar and epoxy-coated, again, in cracked decks. The black rebar, so all of the red dots show that the rebar that is started to corrode. The blue shows no corrosion. It looks like at the chloride content of about 0.03% of the concrete weight, the black rebar started to corrode. And the epoxy-coated rebar, it looked like that corrosion threshold was increased by a factor of about 7. So they didn't corrode until about 0.2%. Even, both in the case of cores that were on cracks or cores that were off cracks. So it looks like the epoxy coating is helping, even in the event of cracking. Okay, so let me wrap up with some of the key observations and conclusions of the work. From the crack density analysis, we learned that a higher compressive strength correlated with a higher crack density. And, really the take-home message is do not over-design excessively. So if we need 4,000 PSI, probably we want to make sure that concrete is not above 5,000 PSI. Over-design is not helping us. The second one is that lowering cementitious materials content to the extent possible, probably through aggregate optimization and so on, and also increasing the cement replacement with SCMs, when it meets other criteria and to the reasonable extent, would result in less cracking. Our recommendation based on this work was to limit the maximum cementitious materials content to 620 pounds per cubic yard of concrete and use the SCMs to reduce the heat, increase long-term resistivity, and in case of having reactive aggregates, preventing ASR per AASHTO PP65. I learned today that this is now changed into AASHTO R80, so it's not a provisional standard anymore. Decks constructed using half-weight procedures cracked 4 times more than decks that were constructed using detours. So if possible, this is the full width should be the right approach or should be the preferred approach. Decks on steel girders appear to crack more, and we'll keep it just as that. And chloride content and analysis, cracks increase the diffusivity by up to a factor of 4. That makes sense. And also epoxy coating was effective in delaying corrosion initiation, not permanently, of course, but even in the case of cracks. Thank you very much.
Question on your research on 4 times the cracking on half width. It's just hard for me as a contractor to understand with all the rebar. Did you have any reasoning why you think that is, whether half width or full width, why it cracks 4 times as much?
Well, there could be a range of reasons. One is that when you do a half-width, first of all, I appreciate the question. When you do a half-width construction, you have the constant vibration of the deck as you are placing the concrete. And especially in the cases where your slump is a little bit on the higher side, you could promote sediment cracking right on the rebar. So that's one reason. There could be other reasons. We didn't necessarily have had opportunity both in terms of time and funding to explore the causes of these observations. We were just kind of looking at different correlation between the cracks that we observed versus different factors like materials and construction methods and things like that.
Vibration makes a lot of sense. That's good. Thank you.
Thanks.
Did you also measure the crack widths, the widths of the cracks?
We did measure, I would say, on a limited number of cases, not on all of the 200 bridges and across the whole bridge. It's that was one of the things that we learned early on in this project is crack mapping on an actual in-service bridge especially is not trivial, and it's quite costly. You'll have a lot of traffic control issues to deal with, and there is a lot of cracks that you have to map and so on. So we try to streamline the process and minimize the time that, for example, a lane was close to traffic and so on. So kind of a long answer of saying we didn't measure the crack widths across every crack. We measured selectively.
Have you done any analysis on those crack widths and find out any correlation between the the width and the diffusion coefficient or the concentration of the chlorides? Because there's two different ideas about the effect of cracking. Some people say that regardless of the size of the cracking will increase the rate of chloride diffusion or the concentration of the chlorides at the rebar. Or the other side says that there is a threshold value that cracks larger than only a threshold value will affect this. And if the crack width is below that threshold value, it doesn't affect the diffusion that much. So I'm just wondering if you have done any analysis of those.
No, that's a very good question. Not as part of this study, but I had a kind of a related research in the lab a few years ago that we looked particularly on how cracking affects mass transport in concrete. And we looked at both permeability, like water permeability, as well as diffusivity in cracked concrete. So on the diffusivity front, we figured out that what's really important is the total volume fraction of the cracks as opposed to the width of the cracks. So the volume fraction in this work would translate into crack density. So how many cracks do you have per unit volume or unit surface of your deck makes a lot more impact than how thick your crack is, essentially because there is not a lot of surface effect that are in play, meaning that the surface of the crack cannot slow down the movement of chlorides significantly. On water permeability, it's the opposite in a way that crack width make a tremendous impact. So there is a kind of a well-known, they call it either a square relationship or cubic relationship, depending on how you define permeability, that your crack widths are essentially your permeability is related to, let's say, a cube of crack width. So if you have a lot of fine cracks, for example, in the case of fiber reinforced concrete, you will have a lot, but the same density, you would get a lot less permeability than if you have one or two big cracks. So I think that, and there is other good work in looking at crack width versus transport that I'll be happy to chat.
Thanks.
One-on-one. Sure.
When you showed your bar graphs, for example, the one with steel girders and precast concrete girders, do you adjust for the age of the bridges that are included in those two groups? Because we know that, for example, the age is very important, especially in early 3 to 5 years.
Right. Well, there were two sets of bar graphs that I showed you, if I go back. One is based on, so for example, these are all based on initial construction. Okay, so all of this data was collected within a span of 2 weeks after placement of concrete. Okay, for the older decks, and including this and so on, for the older decks, you're absolutely right. There is variability in age. I did not present the crack density as a function of age. We actually didn't find a strong correlation between crack density and age. We had some very old decks that had little cracks. We had some young that had a lot of cracks. So it's, and of course at later age you can have other issues, like fatigue or structural or mechanical related cracking and things like that. But we did, so we didn't look at crack density, but we did look at chloride content and whether the incident of cracking had an impact on the chloride level.
Thank you.
Sure.
Hey, sorry, just one quick question here. I really appreciate the presentation. How did you go about measuring chloride at the crack itself?
Measuring chloride at the crack itself is essentially you take a core at the crack and your core is still intact because you have a rebar that kind of is going transfers to the crack, and then you can drill and pulverize the concrete right at the level of rebar. So that's how you get it.
So were you measuring just near the crack or across the full width of the core?
No, it's I would say it's at the it's a small area within the vicinity of the crack. So this sample is not, I mean, I can't tell you if this is a cracked sample or not, but here you have a rebar. Here are the holes that were drilled to extract the powder concrete powder. And if you had a crack that, let's say, you would go down here, you would yes. So yes, you have the rebar. You powder the sample essentially at least half the thickness of the core, if not the full thickness. You extract the powder. You measure the chloride. So if you have a crack that goes here, that's pretty much what we call the chloride level or the chloride content at the level of rebar in the location of a crack.
Okay, thank you.
Sure.
I'm sorry, I just wanted to make a quick comment about, I think one of the first questions was about the possible reasons for the increased cracking density in half-bridge construction. Well, based on my experience, the simple reason may be, or one of the reasons I should say, may be the increased degree of restraint, specifically if you have a bridge deck, or half the bridge deck cast and tied to this first half. What I've seen is that a lot of the transverse cracks propagate from that first half and actually taper off towards the edge.
Right. Yeah, that's a great comment. So the first half would create a lot of restraint on the second half. Okay, thank you.